All right, so this is a little bit of a documentary here, so I just want to show you.
By now, Houston had devised their best shot at survival. They would go for a brief burn before Apollo 13 reached the moon, placing it in the so-called free return trajectory.
All right, so they escape Earth's gravity, and then they have to slow down here, so they have to fire their rockets in the opposite direction. And then now they have to escape Moon's gravity, so they have to fire the rockets one more time.
To drop them into the slot or
and then they also have to slow down one more time. All right, so the animator ended up skipping all those
atmosphere.
All right, the portion that you're going to see is the escape while they're escaping from the Moon's gravity. Okay, so look what happens in the background.
And that we have a safe situation at the moment.
Hey, I want to thank you guys for doing real good work. So are you guys, Jack.
Before Apollo 13 disappeared behind the moon, its landing site on Earth had to be determined. Its present course pointed to a splashdown in the Indian Ocean, where recovery would be difficult. A burn to get them home quicker would plunk them in the Pacific Ocean, within easy reach of the U.S. Navy's recovery forces. The Pacific Ocean it was. As Apollo 13
Notice that they figured out the landing site first.
Sailed around.
They set up their trajectories, not to get the rocket onto those trajectories. Now they are going to try to escape the Moon's gravity.
Vertical burn approached.
All right, now look at the psychology of these people.
The moment of truth arrived.
You can almost sense the anxiety in the room. It's almost palpable. Everyone is kind of nervous. I love the glasses. Everyone has kind of like standard glasses at the time. Entire team of people, whether you need it or not. Again, the same sort of glasses, same type. This guy obviously needs glasses, but he doesn't want to see what's going on. All right, so go for the burn, which means that everybody has to okay this first, and then they have to relay the information. The computations are made.
Okay, we're okay. Fine, down you. We're go fine. Inco, okay?
So they're getting the final okays.
Ground confirms ignition.
All right, so the ignition is confirmed. All right, so here's what I want you guys to do. I want you to count inwardly 1001, 1002, 1003. Okay, now look at the duration of that constant acceleration.
40%. Shut down.
It's about 5 seconds long. It's not 6, it's not 7, it's not 8. It's a precise number. So they experience uniform acceleration for a duration in order to get up onto the trajectory and onto the right speed.
Shut down. I'd say that was a good burn.
All right, so the burns are very short durations, and the uniform acceleration is a short duration uniform acceleration. And then acceleration goes to 0, but it's still a 0. Acceleration is still at a uniform 0 at that point, so the motion is still predictable.
So now we want to power down.
Entering the home stretch, another hurdle. The wrecked service module was still venting small amounts of gas.
All right, so the service module is venting gas, so is that a problem? It is a problem, guys. When you're venting gas, it's going to push you out of that narrow entry corridor. All right, so
with enough force to push Apollo 13 out of its narrow re-entry corridor.
So all of a sudden they discover that it's not on the right trajectory, so now they have to make a correction in order to get the rocket back into the right trajectory.
Houston decided it needed another engine burn.
Okay, so a bunch of computations, and they have to figure out what the thruster is going to be like and how long.
To achieve exact re-entry into the Earth's atmosphere.
We're going to have to do flight. Alex. Ignition.
All right, so the ignition. You got 1 second in.
Thrust looks good. Shut down.
This is about 7 seconds long. This was longer than the other one.
By now, Houston re-entry into the Earth's atmosphere.
Ignition. Thrust looks good. Shut down. Hang in there, it won't be long.
Remarkably, it was the most accurate splashdown of any Apollo mission to date. Helicopters from the carrier Iwo Jima lifted the astronauts from Odyssey. Home at last. As the 3 astronauts arrived on the carrier's deck, the ship's band burst into a rousing version of the Age of Aquarius.
Everything was so nice and predictable, and all of a sudden it turns into a musical. At the end, the human emotion takes over. Notice that what made this so predictable is the fact that they made the entire motion uniform by setting up these constant accelerations all over the place. All right, now let's take a look at this space shuttle launch. Obviously, the NASA makes motion predictable. Within that 8 minutes, you get predictable motion, in essence. All right. The way we will do this stuff is I'm going to make some modifications All right, so go to the problems. Where are the problems? Strange image. All right, let's just go to the problems. Just get out of here. Okay, it looks like we're gonna do problem number 11, but I don't like the way the problem 11 is set up. So I'm gonna make it a little bit more interesting because I want this to turn into a discovery of something which is about to happen. All right, so let's place the problem here. Problem number 11. Cool. And then I'm gonna modify the problem. Okay, let me get the facts of it first. So what do I know? What do we know? Okay, so it's gonna travel 180 miles, so that's a given fact. It says it's gonna take 8 minutes. I don't wanna touch that because I wanna do something else. All right, I don't see all the pertinent facts here, so I'm just gonna copy down pertinent facts, important facts, and then I'm gonna modify some of this stuff. Okay, so what do we know? We know that it's gonna go from 0 to, okay, so what is it, 17,500 miles per hour within a distance of 180 miles. Okay, so that's good enough. And part A of the question, let's figure out the acceleration. And then express it in terms of G's. Okay, so Shelley Anderson said she was pulling 5.5 G's, and that was more than the space shuttle in takeoff. We'll check to see if that's correct. Okay. All right, so let's do the conversions. Go from miles per hour to meters per second. 1 meter per second is 2.24 miles per hour. The other one is this 180 miles. Let me just make space here. It's just to, I messed it up, forget it. I don't want to play with it. The next one is this. All right, so we have to go from miles to meters. 1 mile is 1609 meters. Okay. While you guys are doing the number crunching, let me go get the formulas. All right, so I'll need these formulas. All right, so those are the formulas that we will need. All right, 17,500 miles per hour. What you guys get for that? What's the number?
7,812.5.
All right, so 7,812.5.
Yep.
Meters per second. Give yourself 5 points for that one. All right, 180 miles. What do you get for that?
289,620.
620 meters. All right, 289,620. Give yourself 5 points for that one. Okay, so next step is, so these are the symbols. So which formula do we use? The only one that makes sense to use is the last one, right? That's the only one that you can use. Okay, very good. So now move forward. That's our formula. All right, so final speed squared, the initial speed squared, 2 times a times x, solve for a. All right, so the final initial speed is 0, so this drops out. All right, so we got 2 times a times x. And then get rid of 2. And get rid of x. So here's the acceleration. All right, now the numbers. All right, so the speed is 7,812.5. Square that. And you have 2 times the distance. Okay, so what you guys get?
105.37.
105 and what?
0.37.
0.37? That's too much.
No,
All right,
0.37.
okay, it's 0.37. Okay, now that makes sense. All right, so it's gonna be 0.37. Give yourself 5 points for that one. All right, so, okay guys, what is this in terms of G's? All right, so move this to the left. And when you do that, what do you get?
10.5.
Gs.
Okay, so it's going to be 10.5 Gs, right? Okay, so this gives you 10.5 Gs. All right, so Shelly Anderson said she was pulling 5.5 Gs, and that was more than the space shuttle in takeoff. All right, in all appearance, she ended up lying twice in one single sentence. Or did she? Let's see. All right, we'll have a better idea of if this number is actually realistic when we actually look at the time. Okay, so let's look at the time. How long would it take for you to actually reach this speed at this rate? All right, so let's come up with an expression for time. All right, so T, you got T here, you got T here. All right, so which formula would you use? Okay, either one is good. Yeah, if you're lazy like me, it's the second one. Second one is easier to use. Okay, so let's use that one, second formula. All right, so final initial acceleration times time, and solve for T. Initial speed is 0, so we're done with that. So you got your acceleration times time equals V. Okay, so boom, 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 get rid of A. And here's your time, so it's going to be V divided by A.
I have a question.
Okay, hold on, let's just finish this up. What's V? V is 7,812, 7,812.5. Then what else do we have? We got the acceleration, so that's going to be 105.37. Okay, what do you get?
74.14.
All right, give yourself 5.71. Okay, so converted to minutes, what is this? This is going to be 1 minute and 14 seconds. Okay, guys, what's wrong with this? What's wrong with this is it takes 8 minutes. It takes actually 6 minutes to reach that speed. It doesn't take 1 minute and 14 seconds. If NASA is using a constant acceleration, which they are, how come, if that's the case, it takes 1 minute and 14 seconds? All right, so let me ask you this question. Do you think astronauts can handle up to 10 Gs, 10.5 Gs for 1 minute and 14 seconds? Is that what the problem is? Is that the reason why they don't use 10.5 Gs? Obviously, they're not using 10.5 Gs, so the question is why not? I know they're not using 10.5 Gs in takeoff because or else the entire shuttle mission would have taken only 1 minute and 14 seconds. It takes 6 minutes in reality. Everything combined is about 8 minutes.